Suppose that Roger is currently in Paris on his way to Munich. He then takes the train to Milan. He is now just one station away from Munich, but Roger accidentally takes the train to Barcelona instead. From there, he takes another train and ends up in Paris. Roger ended up where he started, even though he never took a train in the opposite direction. If Roger is not careful, then he may just travel forever in a loop, never arriving in Munich. Loops or cycles are undesirable in route planning, so we would like to avoid them. We can remove cycles by converting the graph to a tree. We don't add new edges since we can't just add new railroads. But we can remove edges from the graph, which just means we won't consider them when calculating the route. Reachability should not be affected. We should still be able to reach all the cities that we could before. The result is called a spanning tree. A spanning tree finds a path to all the nodes starting from some origin. The origin is the root of the tree. In this example, the origin is London, but the origin can be any node. Thus, the tree would look different depending on the origin. Conveniently, performing the breadth-first traversal constructs the spanning tree along the way, so we don't need a new algorithm. Initially, the tree has one node, London. We will represent the spanning tree as a collection of nodes. This is different from a graph, which was a collection of edges. A node has the following form. Value is the node value, and children is the stack whose elements are the adjacent or neighbor nodes. For example, node London with empty children indicates that the node's value is London and there are no children. Initially, the tree has just one node. Next, as with BFS, we first find all the adjacent nodes of the current node. There are two adjacent nodes, Paris and Amsterdam. Paris and Amsterdam are both pushed as children of London. The collection is now node Amsterdam, node Paris, and node London with children Paris and Amsterdam. Paris and Amsterdam are above London because London was pushed first and Paris second, Amsterdam last. Here's the same collection as a table. Next, we move on to the adjacent nodes and repeat this process. Let's start with Paris. Paris's neighbors are London, Brussels, Barcelona, and Milan. London is already in the tree, so we skip it. We add Brussels, Barcelona, and Milan to the tree as Paris's children. Here's the new tree. The next node in the stack is Amsterdam. Amsterdam's neighbors are London and Brussels. Both London and Brussels are already in the tree, so we skip them. As a result, London and Brussels are also not Amsterdam's children. In the new tree, Amsterdam is no longer connected to London and Brussels. Moving on, we now consider Brussels. Brussels' neighbors are Paris, Amsterdam, and Munich. We skip Paris and Amsterdam, then add Munich to the tree as a child of Brussels. Next is Barcelona. Barcelona's neighbors are Paris and Milan. Both are already present in the tree. This also disconnects Barcelona from Milan in the new spanning tree. Next is Milan. Milan's neighbors are Barcelona, Paris, and Munich. Barcelona is already in the tree, so Milan and Barcelona are not connected. Paris is already connected to Milan, and Munich is already in the tree, so Milan and Munich are not connected. Finally, we have Munich. Munich's children are all already present in the spanning tree. The final tree is therefore unchanged from the last one. Here's a video demonstration.